Namaste, I'm Bhaskar Kamble. I had recently started a series of video presentations called Gems from Hindu Mathematics. The last topic I discussed dealt with Vara Samkalita, Chitighana, and the Meru Prastara. In this second topic, I want to start off the discussion with astronomy. Astronomy is a large field, and therefore I will be sticking to some of the topics of my interest, which will hopefully give the viewer a good idea of how mathematical concepts were applied in astronomy. Before I proceed, I want to mention that I am an author of an upcoming book on Hindu mathematics, on the history of Hindu mathematics, which will be published by Garuda Publications. You can follow Garuda at Garuda Prakashan on Twitter, and my own Twitter account is Meru Prastara. Okay, so now the introduction. So astronomy is the study of the motion of stars, planets, and other heavenly objects. Traditionally, it has been that. Today, it is much more, but traditionally, it has been the study of the motion of the heavenly objects as we see them in the sky. And Hindu astronomy is intimately connected with the development of mathematics. In fact, the ideas of trigonometry, algebra, calculus, in fact, the way we use them today, at least trigonometry and algebra, is literally unchanged since it was developed in the formalism of Hindu mathematics. And as far as calculus goes, the main ideas of calculus, infinitesimals, infinite series, ideas of differentiation, summation as integration as a summation, these were developed by the Kerala mathematicians Madhava of Sangama Grama and Nilakantha Jeshtadeva in the 14th, 15th, 16th centuries. So Hindu astronomy provides a vast ocean of beautiful applications of these mathematical ideas. Unfortunately, it can be somewhat difficult, somewhat daunting for someone who has not been involved with mathematics for some time. And it has been my aim in these videos to make it accessible to as many people as possible. And at the same time, preserve the mathematical rigor as far as possible. And this video serves as an introduction to some of the basics which will be important in the upcoming parts. Here is an outline of this part and the upcoming parts. This part deals with the basic notion of the celestial sphere, and it will serve as the basis of what follows. Part 2 will discuss about the celestial coordinates, which are coordinates used to specify the positions of heavenly objects on the celestial sphere. Then I will discuss the simplest astronomical instrument which you can make just by planting a stick into the ground, which is known as the gnomon, and which can be also converted into a sundial. So this I will discuss, and the related notion of how shadows are formed, because the gnomon essentially works on the principle of the shadow cast by the sun. Part 3, I will discuss how the gnomon is used to determine the directions north, south, east, west. And there is a method in the Sulba Sutras, yes, the same Sulba Sutras which discusses the so-called Pythagoras theorem, for determining the directions north, south, east, west using the gnomon. And this is the known as the circle method. Part 4 discusses what I think is the most exciting part of this series, that is essentially a correction to the method, circle method, which was proposed by Prithudaka Swamin and Shripati. This contains some of the most very interesting applications of, and very complex and at the same time very sophisticated application of trigonometry to solve an astronomical problem. And finally, part 5, I would like to give an overview of some of the astronomical instruments that were used in Hindu astronomy and the mathematical theory behind them. And this actually will be based on the work of one very famous historian of Hindu mathematics. He was incidentally Japanese. His name was Yukio Ohashi, and I'll be using his works extensively in part 5. And yeah, okay. So let's start with the concept of the celestial sphere. The celestial sphere, also known as Khagola in Sanskrit, is a very old concept in astronomy, and it is one of the most fundamental and basic ideas which one has to get acquainted with to get a deeper understanding of how mathematics is applied in the field of astronomy. So, what is the celestial sphere? You first consider the Earth, and which I show here in this slide, and you draw the axis of the Earth's rotation, which I show here as the blue vertical line. Now, suppose there is an observer somewhere on the 40-degree latitude. So here I show this observer in the form of this person here, and so you can see this person is somewhere in the European region, maybe in Spain or Italy, which in this case I have taken to be the 40-degree latitude, and then you rotate this whole configuration so that the observer is vertical like this. And the reason for this is that, of course, the observer, wherever they are on the Earth, they consider themselves to be vertical, whether they are on the North Pole, South Pole, Asia, Africa, doesn't matter, but the observer is vertical. Then you zoom out into space far away so that the Earth becomes a tiny point, and then the axis of the Earth's rotation, you just extend it in both the directions infinitely. And you know that the axis of the Earth's rotation, of course, passes through the North Pole and the South Pole of the Earth. Now, with the Earth as the center, you draw a huge sphere of as large a radius as you want. And it is essentially this sphere which is known as the celestial sphere. And the axis of the Earth's rotation, it intersects the sphere in 2 points known as the North Celestial Pole and the South Celestial Pole. These 2 points are collectively known as the Dhruva in Sanskrit. Dhruva is the singular for the pole, and Dhruva is the 2 times version for Dhruva. And then you have also a host of other terminology, but first let me just show a slightly different coloring scheme which I use in my pictures and animations. So the blue circle in the middle is the Earth, and this gray circle is the celestial sphere. And here I have marked the NCP, the North Celestial Pole, and the SCP, the South Celestial Pole. You can see it is a little bit blurred, faded, because it is on the other side of the surface, which is actually invisible. Then there is something known as the celestial equator. You obtain this by considering it is essentially the circle of intersection of the equatorial plane of the Earth with the celestial sphere. So that means you take a plane which contains the equator of the Earth, and the intersection of this plane with the celestial sphere is this circle known as the celestial equator. And then finally you also have something known as the horizon. So the horizon is essentially the intersection of the horizontal plane with the celestial sphere. So what is the point of doing all this? Well, there are 2 reasons. Today we know that the Earth rotates about its axis and revolves around the Sun. This is the so-called heliocentric picture. But ultimately we have to work in a geocentric picture, that is to say in the frame of the Earth, because after all we live on the Earth and we have to find out the positions of all the heavenly objects with respect to the Earth. The second reason is that as an observer with a telescope, you can find out the positions of the objects in the sky, but there is no way of knowing from a telescope how far the objects are. At least with simple telescopes in the early days of astronomy, when people were working with even naked eyes, there was no way of knowing how far they are from the Earth, just where they are located in the sky. This was the information that one had at one's disposal. So we know that for specifying the coordinates of a body, you need 3 spatial coordinates, maybe x, y, z in the Cartesian frame, r, theta, phi in the spherical coordinate system. But as far as astronomical objects are concerned, since we don't take the distance into account, we pretend as if they all lie on the celestial sphere. And that is to say, the distance from the Earth becomes immaterial, and only their positions on the celestial sphere becomes important. And so because of these 2 reasons, the celestial sphere is a very useful concept to observe the motions of the heavenly objects. So that's where the importance of the celestial sphere comes in. And then the meaning of the word horizon also becomes clear, because all the objects that are above the horizon, they are visible to the observer, and anything that is below the horizon is not visible to the observer. So when the sun sets and night comes, it means that the sun has gone below the horizon, and when the sun rises, means it is coming above the horizon, so it is visible. Okay, so the next thing to consider is, so what does the motion of objects look like on the celestial sphere? Remember that in this system, it is the Earth which is fixed, immobile, and all the other objects move about the Earth on the surface of the sphere. Okay, so what is the first? The simplest thing to start this off is the rotation of the Earth. We know that the Earth rotates about its axis from west to east, and which means that all the other objects seem to rotate about the Earth from east to west. So remember, right now we are just considering the rotation of the Earth. Right now we pretend that the Earth is not revolving about the sun. The only motion it is doing is rotation about its axis with respect to the fixed stars. And everything is fixed. It is only the Earth which is rotating about its axis. So what does this mean in terms of the motion on the celestial sphere? Well, since the Earth is fixed in the celestial sphere, it will appear, because of the rotation of the Earth, it will appear that all the stars, all the heavenly objects, the sun, and everything else, they move about the Earth. They rotate about the Earth about an axis joining the north celestial pole and the south celestial pole. So all the objects, they trace out circles, and the circles, the plane of the circles are all perpendicular to the axis joining the celestial poles. And these circles are known as diurnal circles. In this animation, I show the motion of the sun and the stars in the celestial sphere using the Big Dipper and Orion as examples. You can see that the sun and each of the stars move in circles around the line joining the celestial poles. The fact that it's the Earth's rotation about its axis which gives rise to the appearance that all the other bodies are rotating about the Earth was first put forth by Aryabhata in the 5th century in his Aryabhatiya, in his section called Golapada. So this is from verses 9 and 10 in the Golapada, where he states this phenomenon, that it's the Earth's rotation which gives rise to this appearance. And all the major astronomers and mathematicians in ancient and medieval India, they had a section in their works devoted to the celestial sphere. So, for example, Aryabhata had the Golapada, Bhaskara had the Goladhyaya in his Siddhanta Shiromani, and many interesting ideas of trigonometry, spherical trigonometry, were developed and applied to the case of the celestial sphere. Okay, so this is what the apparent motion of the sun and the stars on the celestial sphere would have looked like if the only motion the Earth had been carrying was rotation about its axis. Now we know that apart from rotation, the Earth also revolves around the sun with a period somewhere between 365 and 366 days. So how does this affect the motion of the sun and the stars? Let's consider the stars to begin with. We know that the distance of the stars from the sun and the Earth is so large compared to the distance between the Earth and the sun that this practically makes no difference to the movement of the stars on the celestial sphere, because on the scale of the distance from the stars to the Earth or the sun and the Earth are literally at a single point. So that makes absolutely no difference as far as the stars are concerned. But it's the motion of the sun which is affected because of the revolution. And to understand this motion, we have to introduce the concept of the ecliptic circle and the ecliptic plane. So the ecliptic plane is the plane in which the orbit of the Earth around the sun is contained. So it's the plane in which the Earth is revolving around the sun. This is the ecliptic plane, and the intersection of the ecliptic plane with the celestial sphere is called the ecliptic circle. There's also one more idea which will be useful, is the idea of the zodiac. So we know that the stars in the sky are divided into several groups called constellations. So there are 12 major constellations which lie along the ecliptic circle, and these constellations are collectively known as the zodiac. So you can also call them the zodiac constellations if you want. But this is an idea which is also useful for describing the motion of the sun. Now let's just go back for a moment to the case where the Earth's only movement was rotation about its axis. Then we saw that all the stars and the sun, they move along their diurnal circles along the axis joining the north celestial pole and the south celestial pole. In this situation, the position of the sun with respect to the stars on the celestial sphere remains fixed. So, for example, if the sun position of the sun was somewhere in the Aries constellation, for example, that means that this is where it's going to be for the rest of the time. And just for illustration, I show here this video in which the sun and the stars and also the zodiac constellations are just simply revolving in their respective diurnal circles, and the position of the sun is fixed. It is in the Aries constellation, and this is where it remains for the whole time. So this is the way it's going to look like if there had been no revolution of the Earth about the sun. Right. So now, when we consider the revolution, several interesting things happen. First of all, because of the Earth's revolution, it will appear that the sun itself is moving along the ecliptic circle in the direction of this white arrow. That is to say, it will be in different constellations as it traverses the ecliptic circle. Sometimes it will be in Aries, sometimes in Taurus, Gemini, Cancer, and so on. And then it comes back to its original constellation at the end of 1 year. Now, we have to be careful making the distinction between the tropical year and the sidereal year, but right now we just take it that when the sun comes back to its original constellation, it is 1 year. And well, this is something known as the sidereal year. This is one interesting thing. The second interesting thing is that the diurnal circle of the sun keeps shifting. The diurnal circles of the stars, they remain fixed, but that of the sun keeps shifting. So in this picture, the diurnal circle in the summer solstice is shown as the red circle, and the blue circle shows the diurnal circle of the sun in the winter solstice. And during the time of equinox, the sun's diurnal circle coincides with the celestial equator. And from this you can see that in summers the days are longer in the northern hemisphere of the earth because the sun spends longer time above the horizon and lesser time below the horizon. And likewise the days are shorter in the northern hemisphere when it's winter there because of the reason that it's above the horizon for a shorter time. Okay, so now with these bits of information, we are now in a position to understand how the motion of the sun and the stars looks like when we take also the revolution of the earth about the sun into account. And this here I show here in this animation, in the next animation, and just for convenience I have speeded up the revolution of the earth so that the sun spends only about 2 days in each constellation of the zodiac. It means that the earth completes a revolution around the sun in 24 days. To begin with, the sun is in the Aries constellation. This corresponds to sometime in March or April, and as the sun moves more and more north, you are approaching the summer solstice. Notice also that the constellation Orion is above the horizon, and the sun is also above the horizon at the same time. That means Orion is not visible in the northern hemisphere during summer in the night sky. And the sun is in the Taurus Gemini border, and this is indeed the case for the summer solstice. That is, the sun is in that in that region along the ecliptic during the summer solstice. And as the summer solstice is past, the sun starts moving its journey southwards. So now it is in Cancer and making its way towards Leo, and now it is approaching the autumn equinox or the September equinox that takes place sometime on 22nd of September. And the sun is in somewhere in Virgo constellation, and you see here this animation also indicates that the sun is indeed in the Virgo constellation during the equinox. And the sun now we are approaching now winter, and you see here very interestingly that when the sun is above the horizon, Orion is not above the horizon, and when Orion is above the horizon, the sun is below the horizon. That means Orion is visible in the night sky in the northern hemisphere during winter. And now you are approaching the winter solstice as the diurnal circle of the sun approaches that blue circle shown here. And the sun is now approaching the Sagittarius constellation, and we know that is indeed the case, that the sun is somewhere in Sagittarius during the winter solstice, which takes place around December 20. All right, and Orion remains nicely above the horizon during the night time, and now the sun is coming back from the winter solstice, starts making its way to the north. So now it's in the Capricorn constellation, making its way towards Aquarius, and we are now slowly approaching the March equinox or the spring equinox, which takes place sometime on 20th March, and the sun is somewhere in Pisces during this time. As you can also see in this animation, that the sun is approaching the constellation of Pisces. And well, we have now crossed the spring equinox. Sun is now going towards the Aries constellation, and remember that is where we started from, and so that marks the end of the year. In the Sanskrit texts, there is a whole lot of terminology for all these words that we have been using so far. The celestial poles are, for example, known as the dhruva, as already mentioned. The horizon is called as the kshitij. So one of the words. There are other words. The ecliptic circle is known as the upper mandala, and the celestial equator is known as the nadi vritta. The diurnal circle of the sun is known as the Surya Mandala, and the diurnal circle of the stars is known as the Bhamandala. Bhamandala. There are many other words, lot of other terminology, and but these are some of the ones which are used for some of these common concepts. In case you are wondering how did I plot the stars, the Orion, Big Dipper, and the other zodiac constellations, well, the declination and the right ascension of the stars are publicly available on the internet, and the declination and the right ascension are just these coordinates which you use for specifying the position of the celestial bodies on the celestial sphere. And if you just get these data and you understand how declination and the right ascension work, you can plot them on the celestial sphere. But this probably I will discuss this in the next video. Maybe I should also mention some of the simplifications I've used in the animations. The first simplification is that I've assumed that the Earth goes around the Sun at a uniform rate in a circle, so at a uniform angular velocity. We know in reality that the Earth's orbit is ecliptic, so sometimes the speed of the Earth will be faster, sometimes it will be slower, and this will be reflected in the motion of the Sun in the along the ecliptic circle, in the sense that sometimes the Sun will appear to be moving faster along the ecliptic and sometimes slower. But it happens that this ellipticity of the orbit is very, very small, so the Earth's orbit is nearly circular, and so it does not make much difference for purposes of illustration. The second point to mention is that I've shown here the motion of just the sun and the stars. I've not shown the motion of the moon and the planets, and they are a little bit more complicated because the planets themselves move around the sun, the moon goes around the earth, and the plane of the moon's orbit is tilted with respect to the ecliptic plane and these things. And finally, the third thing to mention is that I have not shown the precession of the equinoxes. So this is a phenomenon which basically refers to the fact that the Earth's axis of rotation traces out a cone once in about 26,000 years. This is something which is on such a large time scale that for purposes of this presentation, you can ignore that. The things that we've seen here will be useful in understanding the ideas that will follow in the upcoming presentations. So like how shadows are formed, the ideas of the gnomon, how the path traced by the shadow of a gnomon, and we can also from these ideas look at interesting things like how to calculate the time of sunrise and sunset for each day of the year given the latitude of the place, and the theory behind the astronomical instruments used by the Hindu astronomers. I hope you enjoyed this and looking forward to seeing you in the next presentation.